Also, as far as the midterm is concerned, it's going to be deadlocks, I mean the material on synchronization that we didn't cover for the test through memory management. So essentially, bulk of it is memory management, but there was this deadlocks and we had the reader writers that we had to get out. So that part and everything through the last lecture that I did in the test lecture. That's material for the test. There will be a review of the material tomorrow in the discussion section. So make sure you attend. I'll put up those slides today itself so you can go prepared for tomorrow.
Monitors were very specifically not on the last exam, so is that something we can expect to be covered here?
Yeah, so I think we had lectures 1 to 8 if I'm not mistaken. So it's going to be 9 through 16 or so. Okay, not counting the 2 class lectures. So every 8 lectures is essentially a test. Yes, so I will have all of that clarified tomorrow in the discussion section. Okay, so today we are going to, as I said, talk about file systems. So we have largely done with memory management. There's a little bit of material remaining that I'm going to cover out of order because I want to do the file system stuff first. Make sure that we are good as far as the lab is concerned, and I'll come back to the memory management maybe next week or something like that. So today we are going to start the next topic. Okay, so we have now covered 2 of the 3 major topics in the course: processes, threads, all of that, synchronization. That's the hardware resources that the OS manages for all of those abstractions in the CPU. We looked at memory management schemes, 4 or 5 different techniques. The hardware that the OS is managing in that case is the main memory. And now we are going to talk about file systems, and then we will generalize that discussion to I/O. So essentially now we are looking at the I/O devices, all of the I/O devices. We'll start with the disk as an example of a device that is really important. It stores all of your data, so we're going to start with that. Talk about files, file systems first. Then we are going to generalize that discussion and talk about I/O devices, device drivers, and all of that. Okay? So that's really a roadmap of where we are going. There's one more component beyond I/O, which is networking. Okay, that's basically RPCs and distributed systems. That's a couple of lectures towards the end. That's not on this slide. Yeah, these are the 3 main components that we will cover. Okay, so here's a picture of what the file system abstraction looks like, okay, from an OS perspective. So as you will see, the file system is not one thing in the kernel, it's actually at least 2 layers. Typically, most operating systems will have support for more than one file system, not just one. Okay, you may have support for, let's say, a native file system like NTFS or HFS in Mac or ext3 or ext4 in Linux. Those are the native file systems, but there are many other file systems supported. If you use a USB drive, it will have a FAT file system. If you use a CD-ROM drive, it will have its own file system, which is an ISO file system or a FAT file system. So typically support for more than one file system in the kernel, but for the purposes of this class, we'll assume there is one. Okay? That's the primary one, we'll ignore the others. And if you look at how that file system component is implemented in the kernel, you see that there are at least 2 layers, maybe more. Yeah, so at the very bottom, you have the disk, which is where all the data is stored. You have this layer here, which is a device-specific layer. Okay, that's really the part of the file system that's going to talk to the device driver. In this case, the device driver happens to be a disk driver. Okay, so the file system has to closely interface with the disk driver in order for it to read or write data. And then there are sort of methods that you use at the device driver level to actually interact with the disk to read and write data to disks and query the status of a disk and all of those. Okay, so that's the device-specific interface. And then the file system itself is implemented, or the part of the file system that's implemented in top is called a device-independent interface. This is the part where you take the data on disk, provide the abstraction of a file, provide abstraction of directories, and allow users to create files, delete files, create directories, and do all of the file operations that you are familiar with. Okay? So there are these 2 layers. And the device independent layer exposes a set of system calls to application. So this is the file system specific system call to open and close files or directories, read and write to files and so on. Okay, so those are all the system calls that the file system is going to export to the higher level applications or end users. Okay? So that's the picture to keep in mind. Okay? Now, when you typically interact with files on most machines, you presumably have an even higher level of abstraction. You don't issue as user read or write calls. You actually work with a graphical user interface, a GUI of some sort, typically. Okay, or you may have a shell where you are going to issue some commands, but those commands or the GUI is in turn going to implement it using the system. So typical end users don't even interact with the OS or files and using the system call interface. They either have a graphical user interface or a higher level abstraction or tools that in turn actually use this interface. So you may be reading or writing files through an editor, for instance. The editor is going to be the one that opens the file for you to issue, read and write when you hit save and so on. So that's the way users actually interact with files. So this is somewhat lower level than what users may actually see. Okay. So as far as some quick preliminaries before we go into how a typical file system may be implemented. Okay, so we'll talk a little bit about what the file system needs to do. Okay, the most important property it provides is persistence of data. Okay, when a user saves data on their as a file on their disk, they expect that data is going to stay there even if the machine is shut down and restarted at a later time. This is called persistence of data. The data persists across reboot cycles. Okay? Very important property. Unlike data in memory that's going to disappear and just shut down the machine, data on disk does not go away. Okay? It stays there and is eventually at a later time. Okay? Now users expect other properties also, the persistence being the most important one. One is speed, which is that you have the ability to go access your data quickly. It shouldn't take a long time to access your data. Okay? Size, okay? There should not be any restrictions on the sizes of files, the number of files in a directory or anything like that that actually matters. If there are any such limits, they should be large enough that for most practical purposes you shouldn't see that there is a limit on how large your file can be. Okay, so you don't expect that. So it should be some limited by the size of disk, of course. You can't have more data than your disk space, but beyond that, you don't expect too many other restrictions. Okay, there are limits, but the limit should be high enough that it shouldn't really make a difference. Okay, when you use it for day-to-day purposes. So sharing and protection is another property. So here you basically provide users the ability to share files with other users by providing the right set of permissions or properties. So you may be able to say this file can be read by others in my group, okay, but not modified, so not be written to but read. Or you can say this file is private, nobody else other than me and my applications need to actually access it. Okay, so you should be able to provide this level of control. Now, when you have personal devices, okay, that you don't really expect other users to access, this doesn't matter. Okay? But when you store your data on servers where other users also have accounts, this matters quite a bit. Okay? So if you don't pay attention to it and you just leave your files in a way that others can freely read it, your data privacy is going to be lost because it allows any other user to go, any other users who has access to that machine to go and just read your file. So you don't want that to happen. So the file system provides features for sharing and protection. And last but not least, you need ease of use. You need the users to be able to go access their files or find their files, not access, find their files quickly. Okay? The old way was you provide a file name that you can remember. Okay? So you basically say lab1.c++, or whatever your file name may be, and then you expect the users to remember. Now we have so many files that just giving a file a name is no longer sufficient. You have lots of data, so file systems have search capabilities. Okay, so you can have in various operating systems a desktop search feature where you can type some attribute of the file, maybe some contents of the file, or maybe some partial name of the file, and the system will search and provide a list of all matches for you. Okay? So those are all features that the file system will provide. So in effect, the file system itself has a small search engine to allow you to find your data. Okay? So those are all requirements that users expect. Now, as far as the system is concerned, which is the combination of the hardware and OS, together this combination needs to support all of those properties that we just discussed. Some of those properties come from the hardware, others are provided by the software in the OS. Okay? So persistence comes from the basic property of a disk drive. Okay? A disk drive is basically able to allow you to put data on it and it stores it until you go and access it at later times. Right? If you switch off the machine, the data on the disk is going to persist. It's not going to go out. So persistence comes from the hardware property. Okay? Speed and size also come from hardware. Okay? If your disks are fast or getting faster, you can get access your data quickly. Okay? The disk sizes will continue to grow. For more than or less than $100, now you can go buy a 2 terabyte disk drive, which is quite a bit of disk space. Okay, so disk sizes keep growing. Okay, so you get a lot of space for not a whole lot of money for your laptop or your desktop. Okay, so some of these come directly from the hardware, others are provided to us by the OS. So the OS also provides a higher level of persistence than just the disk might provide. It may have ability to go and fix data corruption and things like that, which will allow you to increase robustness. And sharing and protection comes directly from the OS of the file system. Okay, this is the property that the file system is going to support. And all of the ease of use is also going to come from file system feature. Okay, so I already mentioned the search facility like Spotlight in OS X. And we have the ability for the OS to mask where your data is stored. Okay, when you create a file, you don't actually worry about where on disk it is stored. You can specify it's in a certain directory, but beyond that, you don't say go put it on this block. So all of the disk space management is hidden from the user. And the OS is going to take care of it for the user. Okay, so that's all coming from the file system. Okay. Any questions on this before we jump into some implementation detail? Okay, so these are just high-level properties that we want from the system and what is done in the hardware and what is done in software. Okay, so now let's look a little bit more. Okay, so I should actually define a file before I talk about file systems. Okay, so you all know what a file is. So I'm assuming that this is not a new concept, but from our purposes, we are going to have a formal definition for it. Okay, so clearly it's a logical unit of storage. It's a container of data. Okay? The formal definition of it, a textbook definition, it's a named collection of related information or data stored on secondary storage. Okay? So what does that mean? So it has a name. Every file is going to have a name, which is assigned to it by the user or the application. That's going to basically, that's why it's called a name collection of data. Collection of data just says it's a collection of bits, bytes, blocks. Okay, it could be some information that's stored in it. And it says it's stored on secondary storage, which means it's stored on a disk that's going to persist data for the user. Okay? That's a formal definition of a file that we are going to use. But you know what all of that means. Okay? Files can contain any kind of data. You can have source file that's source code, you can have binary file that's binary data, and so on. Okay? Now, depending on the file system, the file can be structured or unstructured. Okay? So what this means is some file systems do not care about what is inside a file and don't actually look inside a file to interpret what's in there. Okay? And other file systems actually impose a structure on the file. Okay? Some file systems may not even maintain the type of a file, like it's a Word document, or it's a PowerPoint file, or it's a Java source code. This is not actually maintained by the file system. Another file system may actually track the type of the file. Okay? One reason to track of file type is if the user uses a graphical interface to, let's say, double click on a file, which indicates to the OS that the user wants to open that file. Then the OS needs to know what kind of application can actually open the file. So for that, it needs to know the file type, and based on the file type, it can use preferred application to open files of that type. Okay? Now, if you did not store the file type in the OS, you didn't know what type of a file it was. Okay? Then if you double click on a file, then the OS doesn't know what to do. So it doesn't know what file it is. So what application should it use to open that file is unknown to the OS. Okay? This is one reason why certain operating systems and file systems maintain the file type as part of the file system information. Okay. Now I will mention that Unix file systems actually do not provide an interpretation to what is in the file. They don't even track the file system type at the file or the OS level. So what this means is the file system doesn't know what type of a file it is. So if you want to implement functionality, it says user double clicks on a file, open an application and open the file in that application. That has to be done outside the file system. Okay? Typically, the GUI itself will then have to maintain extra information about file types and so on. It's not maintained inside the OS or inside the file system. And then there are many other types of file systems that will actually maintain this information in the file system itself. Examples being the file system on a Mac, the file system in Windows. They all actually store file types inside the file system. That makes it easier to write higher level applications because this extra information, which is referred to as metadata, is within the file system itself. Right? So all of these issues will come back to. There's just something to keep in mind that files can have types, they can have structure or be unstructured. Okay? As far as structure is concerned, there were file systems on mainframes that actually impose structure. You could say this is a file that is a structured file and each it has a set of records. Records can be of a certain size and so on. These types of files are used by databases. The databases store their data as tables. Tables have records in them. Records have a certain structure associated with them. And when the file system supports structured types, it makes it easier to write a database application. Okay? So there are all these specialized file systems that were written to optimize database performance and so on. Okay? But general purpose file systems typically don't put structure on file, but they will track the type of a file by and large, okay? Except certain operating systems like Linux. Okay, any questions on this? Okay, so I'm not going to go into a whole lot of details on the system calls in terms of how they're implemented. I'll just mention what they are, and then we'll talk about the implementation of the file system itself. So this is, as I said, the higher layer of the file system, which is a device-independent layer, is going to expose a set of system calls. Okay, some of these system calls may already be familiar to you. Okay? There's the create and the delete system call that allows you to create a file or delete a file in the file system. Okay? When you try to access a file for reading or writing, you have to use the open system call. Okay? Open allows you to open the file for reading or writing. Close allows you to close that file. And then you have read and write, which allow you to read and write to that file. Okay? There's another system called seek that allows you to move where in the file you are trying to read or write to. Okay? So these are the standard set of system calls you can use to manipulate files. Okay? Any higher level application that actually you accesses files eventually uses these system calls, even though the user themselves may not use these calls to access files. If you're using Java, C++, or C, you're going to use higher level calls. In C, you'll use the C library. You may use fopen and printfs and scanfs and so on. In Java, you may use the IOStream library or some other library to access files. But internally, all of these systems are going to use the system calls to actually read and write data. Okay? You can, of course, write programs that directly use this system calls, but then you're programming at a much lower level of abstraction. Okay? And then there are many other system calls that allow you to do other things to files. I mentioned the get attribute and set attribute system call. So every file has metadata associated with it, which tracks what's the owner of the file, what's the size of the file, what kind of protection information is associated with the file. We'll see some of that in a moment. Okay? The get attribute and the set attribute system calls allows you to manipulate this metadata. Okay? So if you use Unix commands, for instance, so if you use change owner or change group, okay, so there are commands to change the ownership of a file or the group of a file, or you do change mod, which changes the permissions on the file. All of those will actually be implemented using get and set attribute internally. Okay. So that's a system called interface. And I won't say a whole lot more right now, at least. What I want to do instead is talk about file system implementation. So we will look at how you can go about implementing a file system on disk. Okay? And by and large, we will have to worry about two things. What is the structure of a file on disk within that file system, and how is space allocated for deallocated for the file. So if you answer these two questions, you have at least the first cut of what you need to do to implement a file system on disk. Okay? So we will look at many different organizations where there are different structures for files and different ways to allocate space for files on disk. So before we actually look at that, we need to first understand what a disk is, okay? How it works, because the implementation of a file system is going to be closely tied to what a disk does and how it operates. So first we are going to start with a review of a disk, and then we'll talk about implementing a file system on that disk. Okay, so here's a picture of what a typical disk looks like. You presume you have seen a CD or a DVD. They're still common. Although most people don't use them anymore. Okay, but so what you know about a CD or a DVD is that it's a platter, okay, and then there is data recorded on that platter. Hard disks work the same way. Okay? So typically, what a hard disk is, go think of a hard disk as a stack of CDs. Okay? They're all things. So each hard disk can have 20 such platter. Each platter looks like a CD, okay? And it's spinning inside. Data is recorded on each of these surfaces, as is shown in the picture. This is what a surface of each of a CD, DVD, or a platter inside a hard disk is going to look like. So you will see there are concentric circles, which are called tracks, and so data is recorded on each of these concentric circles. So you will have a number of these tracks, and each of those tracks is partitioned into smaller chunks called sectors or blocks. Okay, so you will see that this is a sector, and that's another sector. So anything between lines, there is a sector. Okay. So typically a track is going to have multiple sectors or blocks. Sectors are the granularity of reading and writing data to a disk. Okay, whether it's a CD, DVD, hard disk, a sector is the smallest amount of data you can read or write. You cannot go any smaller than that. Typical size of a sector may be 512 bytes. So that means that all I/O to that disk has to be some multiples of 512. It can't be any smaller than that. So typically, you are going to have sectors within tracks, and then you have these concentric tracks, okay, which basically are used to record data. Okay. Now, typically, when you have magnetic disks, what is going to happen is you are going to write bits on these tracks. Okay. Each bit is a 0 or a 1. Okay, so if you have 512 bytes, you write 512 times 8 bits on there, okay, on each of these sectors, and then just you're recording zeros and ones, and that's what you are going to read back at some later point to figure out what data you have written to that sector. Is that clear? Okay, so that's the organization of a disk. There are some more things to say, but that's maybe the first thing you need to realize is how data is recorded on a disk. So now, having figured that out, let's take a look at what a typical disk is going to look like. So let's say you have a disk. Okay, so that's basically one surface. As I said, you have to think of a hard disk as a set of platters. So think of them as a stack of CDs that are all on a spindle and they're rotating. Okay, so here you have a disk with 3 platters. Okay, so this disk has a motor in there, and when the disk starts up, it's going to start spinning. Just as when you put in a DVD, it's going to start spinning in your DVD drive. Okay? So your platters are spinning, and the way you are going to read or write data of this is you have something called a disk head. Okay? The disk head is actually something that moves back and forth. So let's say that's your disk head. Okay? And so you have. So your disk head can move back and forth, okay? And then it can position itself on the right track. Okay? So if you want to read data on the innermost track, what you have to do is you have to move the disk head forward so that it actually goes and positions itself on the innermost track. And then it can read or write data from that track. If you want to read data from an outer track, you have to move the disk head back so that it goes back and it moves to the outermost track, and then it can read or write data to that track. Next question.
Is there a head for each platter?
Yes. So I want to mention what's happening on each platter. So this is what's going on for a single platter. There is going to be a disk head on each platter. Okay, because each of these has data recorded on it. If you have multi-layered disks where you can record on the top surface as well as bottom surface, you have a head on the top and a head on the bottom. Okay? Any surface where you have recorded data needs a disk head for you to read or write data from. Okay? So depending on, so here I just showed you a single layer disk, but you can have disks that allow you to record from the bottom and the top. Then you have a disk head at the top and a disk head at the bottom. Yes?
They all spin the same speed.
They rotate at the same speed as
Yeah, do all the platters spin at the
yeah.
same speed?
So the way most of the disks work is there's going to be a motor here. So all of these are connected to a spindle, and this motor is going to rotate, and that's going to cause all the spindles to also rotate. Okay? So the motor is going to spin at some speed. A typical disk speeds may be 4800 RPM, 5600 RPM. Server disks may have 10,000 RPMs. So that means that they're going to spin 10,000 rotations per minute. Okay, it's going to spin 10,000 times per minute. This question.
How do you standardize the size of a block? Because it seems like the outer tracks would have more space.
Okay, that's a good question. Just give me a second. I'll talk about that in just one minute. Something else about the spinning.
So the inside track is spinning faster.
Okay, it's the inside track spinning faster. The disk is spinning, it's going to all spin at the same rate. And think of a wheel of a bicycle you have on there. So if the bike is spinning, what's inside is going to spin at the same rate as the outside. It's going to complete one circle in the same time. Not that there is going to be different speeds for the inside track and the outside track. And you can think of a CD and you spin the CD, the whole CD spins at once.
I think what he was, excuse me, referring to is that the outside of the disk has a higher velocity than the inside of the disk. It has the same period, but it's actually.
Yes. So the rate is going to be the same. We are talking about rotations per minute. But this, the outside circle is bigger than the inside circle, but still going to complete that many rotations every minute. Okay, the velocity is going to be different, but that shouldn't matter. What we are simply asking is what is the rate at which it spins. Okay. Alright, so now we are going to come to this question of what is called recording density. As was rightly pointed out, if you think about a CD, right, you think about the innermost track, the innermost circle and the outermost circle. Okay? You see that the outermost circle is clearly bigger than the innermost circle. So you might think that we could actually record more bits of the outer circle and innermost circle simply because there's more area to write on. Okay? So indeed that is indeed true, but there are two types of disks that you can buy. One is what is called uniform recording density. That basically keeps the amount of data they write on a track independent of the length of the track or the perimeter of that circle. Okay? That basically means that you write 512 bytes in a sector in the innermost track, and you write 512 bytes on the outermost track. It's just that the ones and zeros are more spread out on the outermost track and they're more densely packed in the innermost track. Okay? That's one technology. Another technology makes use of this observation, then there's more area on the outermost tracks. Why waste that space? So let's pack more bits from the outermost track. This is going to result in a non-uniform recording density. Okay, we are getting into hardware details here, but that's basically what it's called. And in that case, what you'll have is, you will not have the same number of sectors on the outermost tracks. You can pack more sectors. Because you record, the ones and zeros are equally spread out, both inside and outside. That means you can write more ones and zeros on the outer track than you can write on the inner track. So you can pack more data. Okay? That's going to complicate the organization. We are going to go with the first of the two options where we are going to assume that you record the same amount of data on any track regardless of the size of the track. Okay, so what that means is as you go to outer track, you have more sparse ones and zeros. Okay, they're spread out more. But you write the same amount. Just for simplicity. But be aware that there are new technologies that basically they make better use of this question.
In a non-uniform this recording density, does the track still operate as the minimum unit of transfer?
Yes, so the question is, in the non-uniform, what is still the minimum unit of trans? So we know a track is not the minimum unit, it's a sector now. Okay? So basically I'm going to draw a picture here. So this is your recording surface. Okay? Let's say that's a track. A track is a circle. Each of this circle is chopped up into smaller pieces, which is called a sector. Okay? So this is the minimum unit you're going to read or write. Right? If you have non-uniform, you'll pack more sector here than you will pack here because there's more area, or not more area, there's more space there. Okay? That's the only difference. But here we'll assume it's uniform and we have the same number of sectors for packets.
Do some OSs prioritize the outer tracks for faster read time?
That's a good question. The question is, do some OSs prioritize outer track for read time? That's really a file system level detail, whether the file system cares about doing those kinds of optimizations or not. If you have non-uniform, it's actually not going to matter because you have the same amount of data in one rotation. So basically, let's say here you have 6 sectors, and here also you have 6 sectors, and then you have the same number of rotations. If it spins 3 rotations per minute, you're going to basically read 3 times that many sectors. So it doesn't matter where you store it. But if you have non-uniform recording, that does matter. And that's an optimization that the file system could potentially use. It complicates the file system. So now you basically have hardware-specific features in the file system, which typically you don't want to. You want to plug in any disk from any vendor and it should work the same. You don't want to write code saying if this is Seagate disk model this versus that disk, do something different. Okay, so you can, but it's somewhat less common, is the way I would put it. Okay, so these are some things about a disk. Now I still haven't talked about how you actually go read and write data. Okay, so let's say the scenario. Let's say you want to read some sector. Okay? The way your OS is going to issue a request to the device driver is going to be saying read, let's say, track 10, sector 7. Okay? Typically, since you have multiple platters, you're actually going to say platter 3. So you say the platters are numbered. Within each platter, tracks are numbered, tracks are circles, and within each track, sectors are numbered. So the way you go and address a sector is you say, go to this platter, which is pick one of these, go to a certain track, which is pick a track within that platter, and then go to a sector. Okay, so that's basically what a read instruction to a device driver is going to look like. Okay? So here there's no file, nothing. I mean, so we are actually at the lowest level in the hardware, where you get a request saying read this data from a file, all of that is going to get translated into something like this in the end. Okay? So then the question is, what is the disk going to do when it receives a request of this sort? Okay? So keep in mind that the disk is continuously spinning. Okay? So essentially we need to go and read that sector from that track and that platter. Okay? So what should the disk do? How should the disk electronics work? Okay? So to actually go and read that particular sector, first you have to move the disk head on that platter to the right track. Okay, the disk head could be at an arbitrary location. Okay, so in fact, let's say that if the disk head is here, because that's where the last data was read from, and now you ask it to move to track 10, which is here, that's track 10, let's say that's track 12. Okay, so you have to first tell the disk head saying go to track 10, because that's where the data is stored. Okay, so the disk head is actually going to move. In this case, it's going to move forward and it's going to go to track 10. Okay? This operation is called a seek operation. Okay? But the disk head is moving to a particular location, okay, which is a particular track. Okay, so that's, and the latency to perform that operation is called the seek time. Okay? There's a time to position the disk head on the correct cylinder. Cylinder is same as a track. Okay? That's a different disk terminal. Okay. So that's called a seek time. Okay. So now let's assume that you move the disk head to the right location. Okay. Meaning the disk controller in the hardware has moved the disk head to the right location. So the disk is now at least on the right track. Okay. But do keep in mind that just because you reach that track, you can't immediately start reading or writing data because you need to, for that sector, to be under the disk head for you to actually read or write data. Okay, the disk is spinning. Let's say the disk is here, and the sector you want to read is actually that sector. So you have to wait until this whole thing is going to spin by and rotate, and actually the sector appears under the disk head. The disk head doesn't spin, the platter spins. Okay. So once the platter spins and the sector appears under the disk head, that is when you can actually read or write data to that sector. Okay. So once you have moved the disk head to the right track, you still have to wait for the sector you're interested in to spin by. Okay. This is referred to as rotational latency. That's a delay because you're going to have to wait for the right part of that track to be under the disk head, and that's another delay. Okay. So whenever you read or write data, you're going to incur a seek latency, you're going to incur a rotational latency. Only after these two things have happened can you actually read or write data. Okay? So disk seeks and rotational latency is wasted time. The disk is not actually doing anything useful. It is simply trying to position the head and wait for the right sector to appear under that. Okay? So once you have actually managed to do all of those two things, then you can do disk transfer. Okay? So that's basically going to allow you to read or write. So what this says is that the typical latency of a so disk latency is going to be a seek plus a rotational latency plus a transfer time. Okay, so this is the time it takes to service a disk request. Okay. The typical time to service a disk request involves a time to do a seek operation, time to for rotational latency, and then the transfer time to actually read or write that sector for some number of sectors that you may want to read or write. Okay. But just to put some, yes, your question.
On each disk, there's multiple platters, and each platter is multiple tracks, and each track is multiple
Sectors, yes. That's what the picture, so just put the picture back, which is the same picture here, but this may be more clear here. So that's showing just one platter, but typically you will have more than one, you have 10 or 20 platters. So that's showing the cross section of a platter. So you have these tracks, which are circles, okay, and then within a track you have sectors. Okay. So that's the latency of this operation. Now just to put numbers on these operations, so typical time to perform a seek is in the order of a few milliseconds. Okay. It can be anywhere from 1 to 10 milliseconds. The typical time for a rotational latency is also in milliseconds. Again, it may be a few milliseconds. Okay, so let's say it's 5 milliseconds. It's for simplicity, let's say it's also 5 milliseconds. And the transfer time depends on how much data you're going to read. Okay, one sector may not take a whole lot of time. It's going to be significantly less than a millisecond in this case. So what this tells you is lot of time is wasted in seek and rotational latency, and the actual useful work that the disk is doing in reading and writing data is only a small component of the total disk I/O time. Okay? So that means if you just look at the number. So typical disk I/O time, this is why we said it can be on the order of 10 milliseconds or so. This is why it's 10 milliseconds, because you're wasting several milliseconds doing a seek, several milliseconds doing a rotational latency, or incurring the rotational latency, and then maybe a millisecond or two doing the transfer time. Okay. The other thing to keep in mind is the disk seek time and the rotational latency is a variable parameter. It's not going to be fixed. Okay. The seek time is going to depend on where is the disk head now and what track am I actually wanting it to go to. Okay. The worst case for a seek time is that the previous operation left the disk head on the innermost or the outermost track, and then the next I/O is actually at the other end of the disk. So you have to then do a full scan across the entire surface of the disk. Okay? That can take you the worst case seek time, which can be on the order of 10 milliseconds. Okay? Because this is a manual operation. Okay? The disk head is a mechanical device that a motor is going to slowly move the disk head forward and backwards. Because this is basically how it is going to work. So you have to actuate the motor and start moving the disk head, and then once it reaches the right position, you have to stop the motor so that it is stationary. Right? So that's a mechanical operation. It takes time. So that's the worst case seek. Okay? Same is the rotational latency. The worst case rotational latency is as soon as you reach the right track, the sector that you're actually interested in has just spun by. Okay? So now you have to wait for an entire rotation for it to come back under the disk. Okay, that's your worst case. Okay, entire rotation is going to be the worst case for the rotational latents. Okay? Typically you won't see the worst case, but that's basically what you might see in certain cases. Okay, but the point is it's variable. It depends on where is the disk head, where does it need to move to, and once it moves there, where is the sector it's interested in and how long will it take for it to swing. It could be anywhere on the concentric circle with respect to the disk head. Yes, question.
How does the head know, things like what sectors are beneath it, or like where the platter is?
It's a good question. So our question is, how does the head know what platter is beneath it? Right? So the way you are going to have to figure this out is you are going to put some markers between the sectors that identifies, like saying this is sector 1, sector 2, and so on. So there are some markers. So once you reach the right track, you're going to actually start reading data and try to read markers so you know what sector is spinning by. Okay, so that's how you. Otherwise, there's no way because the data is just bits, ones and zeros. You don't know what sector number it is. So you're going to use the markers to figure this out. Okay, that's all hardware, electronic stuff. Any other questions on this? Okay, so why are we talking about all this hardware? This is important from a file system design standpoint because the performance of your file system is going to depend on what kind of I/O performance your requests are going to see. Okay? So if you organize your disk space such that every time you try to read or write data, you are going to incur a lot of seek and lot of rotational latency, your performance is going to be very slow. Okay? Because this is, as I said, wasted work for the disk. Okay? But on the other hand, if you lay out data on disk for files such that when you do file I/O, the rotational time and the seek time is minimized, you are going to see better performance. Okay? This is why all of this is important to understand how a disk works, so you can optimize what is really wasted overhead from the perspective of the file system. So to get high throughput, get good disk speeds, or disk speed, read and write speed, you want to somehow reduce this part of the I/O latency as much as possible. Okay? Any file system organization that's going to do that will provide better performance to its users. Okay, so the question is now, what do we do to optimize it? That's what's coming next. But this is why all of this background was important to understand. Yes?
How does that apply to solid state? How does that apply to solid state drivers?
That's a good question. So I haven't mentioned solid state. So the question is, how does this apply to solid state disk? So first of all, you should ask what is a solid state disk. You've probably heard of solid state disks. They are called SSDs. Okay, so those are all disks that have no moving parts at all. Okay? A solid state disk is like RAM. Okay? In RAM also there are no moving parts. You just say go to page 10. Okay? And you can basically go access whatever data you want. Okay? Same is true of solid state disk. There are no moving parts. It's just an array of bytes or array of blocks. You can instantaneously go to any block and access any data you want. Okay? So there is no seek, there is no rotational latency. You just say, go to this block, you go and pull that block out. Okay? So none of what we are going to talk about here actually is going to apply to solid state disks at all. File systems have to be completely redesigned to work with solid state. In fact, if you try to put this optimization, they make no sense on the solid state disks. Because you're trying to optimize something that doesn't even exist on SSDs. Now, on that side, solid state disks have other problems, which basically says that each block has a lifetime in terms of number of read or write cycles. If you continuously overwrite a block, after a while the block is dead. Basically, there's no recording capacity left on it anymore. So you have to do a whole set of new optimization, which is you want to spread your write requests as much as possible. But each block is going to have an age. Age is how many times it has been used. After a certain age is reached, that block is dead. Okay, so you don't want certain parts of your disk to die faster than other parts of it. Dead doesn't mean that the disk is dead. It just means that that block cannot read or write with high accuracy anymore. So you have to stop using it. Okay? So you have to do all sorts of other things for solid state disks. So file systems have to be redesigned. So none of what I'm going to talk about here is going to apply to SSD file systems. But I'll have something to say about that again after we have gone through the discussion. Okay? Is this clear? Okay, so now having talked about disks and disk overheads, okay, so now I already mentioned all of this. So there's the disk platters and whatnot. So let's ignore all of this and move on. Okay. So now let's talk about file systems. Okay. So we are going to start with some very simple examples of what file systems are. We'll look at the performance of that file system, of that organization, and then we'll move on. Okay. I'm not going to take any particular file system from any particular OS, but rather general principles of how many of those file systems are designed. Okay. And I'll mention what organizations are used in what context. Okay. So the first thing is every file system needs to basically, so the file system has files. That should be clear. We are going to ignore directories for now. Okay. Directories add a layer of complexity that we just ignore. Okay. So let's assume a file system has n files. Okay. The job of the file system is if a user comes in and says, I want to access file 10, okay, and I want to read this block of the file, it should be able to figure out this file has this block stored on this sector of the disk. That's what it needs to do. Okay. So just as page table said, if you want to access page 10, what frame is it stored in? Here we are going to maintain a structure which says if you want to go and access file foo and the 10th block of file foo, which sector should I go and read and write it? Okay. So that's the basic mapping you are going to mention. It should basically here. So you are going to have this mapping which says file 0, block 0 is basically that platter, that track, that sector, and this file, the next block is on that track and sector and all of that. Okay. You will see that files here are numbered. Okay. And the reason for this is internally, although files have names, okay, internally every file has a unique ID or a number. The operating system doesn't use names. Once you give it a file name, it's going to just translate it to the unique number for the file. And internally it works with file numbers. You don't actually have file names inside. That is only for the user. Okay? Because you don't want to remember files by numbers. That doesn't work for people. Okay? You like to give names, but the OS doesn't care. It doesn't care about the strings at all. It just uses that to figure out what the ID of the file is. Each file has a unique ID, which is an integer associated with it. And then you basically go and access that file, okay, through that mapping that the file system is going to keep for. Okay. So then the question is, what kinds of organization should we use? Okay. And for that, we need to basically answer a few questions. First of all, you need to be able to support both sequential and random access to a file. Okay. When you create a file, users like to access them in any way they want. They don't want the file system to go ahead and have any restriction. So what that means is if you want to jump to a certain location of a file and just read that part, that should be allowed. If you want to read the file sequentially from the beginning to the end, that should also be allowed. So we basically want to support both sequential access as well as random access to a file. Both of them should be done efficiently. We need an efficient data structure to maintain that mapping. That's a mapping that you're going to maintain for each file. Okay, so metadata information. And then you have to figure out when you create a new file or files grow or shrink, which blocks or which sectors of the disk to assign to that file. Just as in memory management, we assign frames to pages, here we are going to assign sectors or blocks. We are going to use that term interchangeably to files. For a file, you need a file with 3 blocks. You have to find 3 unused blocks or 3 unused sectors and allocate it to a file. Okay. So we want our file system that needs to answer these 3 questions, these 3 basic questions. And then we will basically have a rudimentary file system. So before I actually describe the file system organization itself, we want to basically have some preliminary. So first is just as you had a page table in memory management scheme, here we are going to basically have a data structure called the file descriptor. Okay? File descriptor is metadata information. In the Unix world, it's called the inode, index node. If you've heard of the term inode, you know what I'm talking about. Okay, the file descriptor stores all of the information for that file that the user or the OS needs to access, including the owner of the file, the permission in the file, as well as that mapping that I just mentioned from block numbers to sectors is also maintained in the file descriptor. So that you'll see different organizations for the file descriptor, and that will have impact on performance and then the. Okay, so key data structure that the file system needs to maintain for each file is a file descriptor. Just as you had a page table for processes, we have file descriptors for files. Okay. Now, here are some other observations. Here are some other observations we can use to design our file system. Okay. First observation is most files are small. Okay. So if you take a typical hard disk, okay, analyze all the files on that disk, okay, you will observe that by and large 80 to 90% of the files are going to be very small. Okay. They are median size, or not median, mean size is going to be on the order of 2 to 4 kilobytes. Okay. This could be small configuration files that the OS creates, all sorts of small files. Okay. So a large number of files are going to be very small in size. Okay. But most of your disk space, okay, is going to be consumed by a small number of large files. Okay. All these small files don't consume a lot of space. Okay. But what actually consumes space is a small number of very large files. Okay. Maybe you have a movie stored on your disk. Maybe you like to take lots of photos. Okay. Each JPEG image may be 8 megabytes in size or 10 megabytes in size, and then you have a bunch of them and they start chewing up space. Okay. So that's an observation to keep in mind. Most files are small. Most of the space is taken by a small number of large files. And so we need to design our file system to address the needs of both small files as well as large file system efficiently. Okay. So IO operation should target both small and large files, and we need to somehow provide good performance for both kinds of files. So these are all observations that we will use when designing our file system. Okay. So first file system is really very straightforward. It's called contiguous allocation. Okay. So what we are going to do here is the OS is going to maintain, or the file system itself is going to maintain a list of all the free sectors on your disk. Okay. So you're going to maintain a list which says that sector is free, this sector is free, this sector is free. You're going to have this list of unused sectors on the disk, unused disk space. Okay. So when you create a file, okay, you are basically going to allocate a contiguous chunk of sectors to that file. Okay, so if you want to create a file, that's each sector, let's say 512 bytes. If you want to create a file of up to 1K, you are going to allocate 2 contiguous sectors. If you want to 2K file, you will allocate 4 contiguous sectors and so on. So in this case, files are going to be stored contiguously on disk. Okay, so that's your disk. This is your disk, and you have a 2 sector file is going to be stored this way. So if you have another, let's say, green file which needs 3 sectors, you find 3 vacant sectors, and then you're going to lay it out there. Okay, so that's block 0 of the file, that's block 1, and that's block 2 of the file. Okay. So this is contiguous allocation, very straightforward policy. You can maintain a list of unused blocks. When you need a certain number of blocks for that file, you just look for a contiguous sequence of those blocks, unused blocks, and say this is where this file is going to be stored, and you're done. Okay. When you delete the file, those blocks are returned back to the free space, free list. So basically the free list is going to track unused blocks, and all the other blocks are going to be assigned to some file or the other. Okay. The file descriptor is very simple in this case. The file descriptor only needs 2 pieces of information, which is where is the beginning of the file. Okay. So that's the start. And how many blocks is the file? Okay. What is the size of the file in terms of number of blocks? If you point the beginning of the file and say the block file is 3 blocks inside, you can then figure out that these are the 3 blocks. Because you know the start address and you know the address of the others. Since they are all contiguous or sequential, you can figure out the address of any block. Yes.
Now, when you say that the file is 3 blocks in size, does that mean that we then need to translate between like blocks and sectors to
Yeah. So in this case, we assume that one block is one sector. Okay. In real file systems, that's not the case. Sectors could be some multiples of blocks, but for simplicity, we'll assume our file system equates a sector to a block. That's the simplest organization. So if the sector is 512 bytes, a block of the file system is also 512 bytes. File systems deal with blocks, disks deal with sectors. In this case, we are using them interchangeably. Okay? So if you want 3 blocks, you are going to assign 3 sectors and you are done. Okay? Yes, question they have here.
Sequential block.
Yes, because this is contiguous allocation, they have to be sequential.
So like the first block was edited, the second block is not. And that's what we're looking for.
Yes. So basically what you are going to do, the way this is going to work is you have this free list. Okay? Yeah, let's assume the free list is maintained in a sorted fashion. So it's going to say here, I'm just going to number them. Okay, so it's going to maintain all the sectors that are unused. Okay? So you just find a run that is large enough. Find a sequence that is large enough and you say that's where the file is produced. A contiguous sequence, a sequence that's long enough to accommodate the file. So every time you want to create a file, you're going to scan this free block list, find a sequence that's big enough, and that's where you put it. Okay? So that's contiguous allocation. Okay? So the advantage is the most straightforward organization. Okay? So nothing much to do other than to maintain a free block list that's sorted, and then every time you create a file, you scan it, and you delete files, you return blocks back to the free block list. Okay? File descriptor, very straightforward. You just have entry to the beginning of the file and the size of the file. You can figure out where the file belongs. Okay. Access time. Okay. But I/O latency is also not bad because you are going to basically incur to access the file. You are going to incur one seek, okay, from wherever the disk head is to, let's say, the beginning of the file. And from that point on, sequential access is just keep reading. There are no more seeks because the file is stored continuously. So there's one seek to the beginning, and then one rotational latency, and then you can read the entire file. Okay, continuously. So our performance for both sequential and random access is good. The random access is the same thing. You're first going to use the file descriptor to figure out where you want to go, and then you do one seek, one rotational latency, and you're there. And then you're basically going to read that block. Okay? So all of that is good. What is not good is all of the problems we saw when we did contiguous allocation of memory. Okay? You should immediately say this is going to cause fragmentation. Okay? As you start creating and deleting files, over time, your free block list is going to be scattered. It's going to have all these holes. You want to create now a large file, you may not have a contiguous sequence of holes that's big enough to accommodate that file. Okay? So you're going to have external fragmentation is bad in this case. Okay? So that's going to be one problem. Handling changing file sizes is another problem. If you allocated 3 blocks, now you start writing, let's say you're writing your lab, whatever, 2 or 3, and you wrote some new code, and you hit save, the file size increased. So you need one more block, but there is no block that's adjacent. You stored another file. Now you're in trouble. You can't increase the block, the file size. You have to actually move that entire file to another location on this. Very wasteful. Okay, so you can't handle changing file sizes very easily. There's this fragmentation. Okay. Now, needless to say, because it's so straightforward, very old file systems use this organization, but no more. You don't want to deal with fragmentation and run these defragment and so on. Except in one case where it's actually used all the time, and those are basically write-once disks. Write-once disk meaning CD-ROMs or DVD-ROMs. Okay? Because you can't change files once. You burn the CD once and you're done. Okay? So when you burn the CD the first time, you can just lay out files in this fashion. You know what files are going, you just lay them out, you burn the disk and the file doesn't change after that point. So you may as well take advantage of this very simple organization and be done. Okay? Because nothing changes on a CD once it's burned. Okay? So CDs and DVDs still use this organization because it's straightforward and if the set of files is static, okay, then it's a good organization. If you have dynamics where files come and go, it's not so good. Okay? Alright, so next. Yes, your question. Okay, so next organization is a linked list organization. So that's shown in the picture here. So in this case, what we are going to do is we are going to relax the assumption that the file needs to be contiguous, because that causes fragmentation. So we now allow the blocks of a file to be scattered on the disk. Okay? So block 1 could be on one track and block 2 could be somewhere else and block 3 could be somewhere else. Okay? So anytime you need a block, you just pull any sector and you can add it to the file. And the way you are going to actually organize the file is you actually have a linked list. Okay? On disk, not in memory. It's not a memory linked list. This is a disk linked list. Okay? So the way it works is, this is your sector. Okay? Let's say it's 512 bytes. Okay? You should reserve the last byte of that sector to store the pointer for the next block. So if you have 512 byte sector, you're going to give 511 bytes to the file itself to store data. In the last byte of that sector, we're actually going to store the address. It's not the last byte, it could be the last 2, 3 bytes. So in this last byte, you're going to store this information. Okay, so that tells you the next block is here. So the platter 2, cylinder, cell, etc. So that's again the data. And the last byte is going to store the address of the next block of the file and so on. So you construct your file as a linked list on disk, and then you're going to store pointers to the next block also on disk in the data itself as the last block of the sector. Okay, is that clear? So the file descriptor again is going to store a pointer to the head of the list, which is basically the first block of the file. So that's going to be stored in the file descriptor. So to read the file, go to the file descriptor, you read the head of the file, and then sequential access, you go read that block, then you look for the next address, and you issue a request for the next block, you read that block, look for the next address, issue this request for the next block, and so on and so forth. And this is how you are going to actually access data. So early versions of the DOS operating system, okay, used a linked list organization. Okay. The FAT file system, if you have heard the term FAT, which is a file, stands for file allocation table, used a linked list organization, early version. The more sophisticated ones have other variants, but the very old versions of FAT use this organization. Okay. So the free space, the nice thing about this is the free space on disk is also stored as a linked list. It's a special file that consists of unused blocks. Okay, so any block is either on a file list, linked list for a file, or it's on this special file called the unused space file, which is basically all the unused blocks. You also store them as a linked list. Okay? So to delete a file, all you're going to do is take the head of the block and add it to the linked list, and then add a pointer to the rest of the linked list. And you're done. Okay? Or you can just take this and add it to the tail of the linked list, so the linked list is going to do. So deletions are very straightforward. Okay.
It seems like the fragmentation would be a lot worse with this implementation.
Okay, so for its fragmentation works. So first of all, you have to realize that you are no longer requiring these blocks to be contiguous. So external fragmentation will not exist in this case. Okay? External fragmentation simply means you want to store a large file. You can't find contiguous space because there's no hole that's big enough. Okay? Blocks are going to be scattered on this. That doesn't mean it's fragmented from our perspective. It just means that blocks are not contiguous.
Can two files share a sector?
Can two files share a sector? So we typically do not allow blocks of a file. This will belong to multiple files. We don't need one file. Okay. Right. So performance sequential. So now you should realize why this performance is going to matter. Okay? Because in this case, if you are going to read the file sequential, each block is going to incur one seek, one rotational latency, and one transfer time. Okay? In the contiguous allocation, the entire file had one seek and one rotational latency, and then you could just transfer the entire file in one shot. Here you are going to read each block. The block is scattered. So you may go here and read the first block, then you seek somewhere else, read the second block, seek somewhere else, read the third block, and so on. Okay. So if you have n blocks, you are going to incur n seeks and n rotational latencies. Okay. So the performance here is going to be much worse than the performance of contiguous allocation. Okay. The second problem is this is a linked list. Okay. So random access is going to be bad. So if I say give me the 10th block, the only way you can even figure out where the 10th block is stored is you have to read the first 9 blocks to find the address of the 10th block to begin with. There is no other place the addresses are stored, they are stored in the file itself. Okay, so essentially, random access degenerates to linear scan. Okay, so random access is also poor performance. Okay, so to read the ith block, you're going to incur I seeks, not one seek. And to do sequential access also, you will basically have incur seek and rotational latency for each block. Is that clear? Any questions on this? Yes.
In a 2 terabyte disk, what would be a sort of reasonable upper bounds for like platter number, cylinder number, and sector number?
So the question is, in a 2 terabyte disk, what could be the reasonable size of platters and so on? So first of all, it depends on the number of platters. Typically, you may have on the order of a dozen to 2 dozen platters. Okay. Then also depends on the size of the disk. If you have a 2.5 inch disk versus a 3.5 inch disk, the 3.5 inch disk are bigger platters. 2.5 inch discs are smaller platters. So if you have smaller platters, you can pack fewer tracks. But there's an order of several thousand tracks per platter. So that's basically the way to think about it. And several hundred sectors per platter. So typical sector numbers will go from 0 to a few hundred. Track numbers will go from 0 to maybe 10,000 or a few thousand. And then platters go from 0 to 10 or 0 to 20.
Okay. I was just wondering like about how much space the pointer would take up.
So you can think of it as 3 integers, but you don't have to have 32-bit integers. You can have smaller integers. Okay, so that's your linked list organization. Okay, and so there are some good things and some bad things about it. Okay, and we already talked about them. And the last organization which we are going to talk about is indexed files. Okay, so what is going to happen here is we will retain the advantage that the file doesn't have to be contiguous because that eliminates fragmentation for us. But what we don't like about the linked list organization is the block addresses are stored in the file itself. To get to the ith block, you have to read all the previous blocks to figure out the address of the block. Okay, so what we are simply going to do is pull the addresses out and store them in a file descriptor. Let's say index. Okay, so basically you have an index here which basically shows the address of each block, just as you had a page table. Okay, so you have a table, it says where the block is. So if you want to read the 10th block, you look at the 10th entry of this table and you'll know which cylinder and which track and which platter and which sector it is. Okay. So initially you have to go and read the entire file descriptor, which is stored in some special location like this. Once you have read the file descriptor into memory, anytime you need to read or write some block, you are going to look at the corresponding entry of that file descriptor. So now you know the disk address of that block to go and read that and write. Yeah. So blocks are no longer contiguous like before. You can allocate any sector to any block. Yes, question.
So that each track has its own
Question: each track has its own file descriptor. Is that your question? So the file descriptor is a per file data structure, not a per track data structure. Okay, so the way it will look like, this looks messy. Let's say you have file foo.java. Okay, so that's a file descriptor for that file. Let's say it has 3 blocks. So it's simply pointer saying this is going to point here. This is going to point here. This is going to, so wherever you allocated blocks, you're going to pointer. So this is going to say track 3 sector something. This is going to track 10 sector something. So that's what you're going to store here. So if you want to read the 3rd block, you're going to simply read the file descriptor, look at that entry that tells you the address. You issue a read or write request to that address, and you can read or write it.
So would this mean that at the end of each file we will not need a pointer for the next block of memory? Because we can just have a file descriptor and move from empty blocks to file descriptor from like hoping like a stack structure on the empty blocks and just keep popping to the file descriptor as we need blocks.
Yes, so in this case, as you pointed out, there's going to be a free list that keeps track of all unused sectors. If your file grows, you can pull any entry of that list and just stick it here. And then you have one more block in your file. If you want to delete some blocks, you just release those and put them in the free block. They don't have to be contiguous, simply have a file descriptor that you can keep growing as you need to. Okay, so this is the index organization.
Where do you store the array?
Where do you store the array? Okay, this is a file descriptor. Okay, it has an array in it. So this is called metadata for the file. Okay. So the metadata for the file is stored in a special region on disk. So so this is where all the file system organization comes into play. So let's say you have your disk here. And for simplicity, let's say it's one platter. So when you format your disk, okay, what is actually happening during the format process is it's going and reserving some region of the disk to store all the extra information for metadata information. So it is going to create these empty file descriptors and put them in a special region. In Unix, this region is called a super block. Okay? So you always have regular block and super block, just as your users and super users. Okay? In your file system, you are going to have some number of super blocks. Super blocks are reserved for storing file descriptors. They cannot store data from a file. They only store file descriptors or inodes of the file. Okay? So when you create a file, you are going to actually go to the super block and pull out an unused file descriptor, an unused array, and assign it to the file. Okay? And the reason files are numbered is basically each file descriptor has a unique number. Okay? So if you basically allocate 10 file descriptor 10 to a certain file, that file gets numbered 10. Okay? So the number of the file is actually the ID of the file descriptor that was assigned to. Okay? So in Unix, if you actually do ls minus I, you can actually figure out the inode number or the number of a file. Yes, I can show you. I can pull up a terminal here. So if you actually do ls minus I, you'll see that there are numbers appearing next to files. Those are the inode number. That's the ID of the file descriptor that's been assigned to, in this case, their directories, but it's the same concept applies. Whether your files or directories, your inodes or these file descriptors assigned to them, and they have IDs. Okay? And the important part is the file descriptors themselves are stored in a special region of the disk called superblocks. Okay? Because you need to be able to find the file descriptor in order to access the file. So the file descriptors have to be known to on disk. Okay? So I'm going to mention one last organization quickly, and then we will. Okay, so very quickly, the advantages and disadvantages: no fragmentation, sequential random access are both efficient now. You just have to read the file descriptor. Sequential access basically gives you all the addresses you issue request. Still one seek and one rotational latency per block. The blocks are scattered, but at least random access is better. You don't have to do a linear scan. You can just go look up the index and go read that block. Okay. Now, disadvantage is sets the size of the maximum, so sets a limit of the maximum file set. If you allocate a file descriptor with 100 entries, that says your file can only have 100 blocks. File descriptors are known to be a fixed size. You can't have arbitrary size. So you have to predetermine when you format the file system what's the maximum size of the file you want to support in the file system. You create empty file descriptors of that size. That's going to put a limit on the file size. And that's the size of the file descriptor. Okay. We somehow want to get rid of that restriction. And that's the restriction with this organization. Okay. So I'm going to mention quickly one last one, and we'll come back to that later. Okay, this is called a multi-level index. Rather than one index, we are going to have multiple levels of indirection. Okay, so this is your file descriptor here. Okay. And the file descriptor will use a different organization depending on the size of the file. If your file size is less than 12 blocks, okay, the first 12 blocks are just direct pointers to disk blocks. Okay. When your file size grows to 13th block, other than storing the pointer here, we are going to create another index block, and then we are going to store the next, and let's say the index block can store 1024 entries. The next 1024 pointers are going to be stored in that index block. And then if the file system goes beyond 1024 plus 12 blocks, we are going to create what's called a double indirect block. So create an index block that itself has pointers to other index blocks which are going to point to data. Right? And you can also have a triple indirect block where you have one index block that points to two other index blocks and then basically point to the data. As the file size grows, dereferencing your block requires multiple levels of indirection. Right? For small files, all the block pointers are in the file descriptor itself. As the file size grows, you have to traverse multiple index blocks to get to your data. Okay? So you penalize larger and larger files, but keep the performance optimized for smaller. That's the philosophy. This is the data structure that most Unix file systems actually use. And that's the file descriptor in Unix. It's called an inode or an index node. This is how it actually works. So we'll come back and discuss this again next time. And I won't stop here.